Hello everyone, and welcome to the Turning Effect Post Lab. So, we found that the turning effect depends not just on the amount of force that you apply, but also on where you apply that force. And in this case, we called that the lever arm, the perpendicular distance from the axis of rotation to the point of application of the force. So in using our equal arm balance device that we used in the lab, if we set it up so that things were balanced, notice it's horizontal here, right? We had a turning effect due to this lever arm for this mass and on this force of gravity. In this case, it's a force of gravity, so it's m1g, right? And this was the lever arm. And then over here, and that was clockwise turning effect, because if it was the only thing it would make it rotate clockwise. Over here is the second lever arm and the second force of gravity, a bigger force of gravity because there's more mass here than here, so it weighs more. And this is a counterclockwise turning effect because it would make it rotate counterclockwise. So different directions on these. And these were, of course, balanced, equal in magnitude. So, in the end, what did you figure out you had to do with the force in the lever arm to create a turning effect? Right? What combination of force and lever arm worked here? Multiplication. Right? In order to get things to balance out, you had to multiply R times F, or lever arm times the force. Okay? So RF is turning effect. Now, turning effect is not really what we call it in physics. Turning effect is just kind of more of a descriptive name. In physics, we call the turning effect a force has, depending on where you apply that force, torque. Might be a term you've heard before, right? Torque. It's denoted in an equation by a lowercase tau. Tau is a Greek letter, right? If you notice here, it looks like pi with just one leg. Right? So it's that kind of Greek letter, all right, but it's just got the one leg on it here, kind of more in the middle than pi, okay, but very similar looking. So you'll start seeing taus pop up now for torque. You got to be careful that your taus don't look like t's, right, because that's time or period or whatever, and we don't want to confuse them, so tau, right? So we're going to start calling it torque instead of turning effect, but that's what torque provides, right? It's the thing that makes stuff rotate. And don't forget here that R perpendicular is the lever arm. As I said, that's the perpendicular distance from the axis of rotation to the point of application of the force. And so in this early iteration here, we're going to calculate torque by taking lever arm times the force. The units for this come right from the equation. Note that the units of force would be newtons, and the units of perpendicular distance would be meters. So the units are Newton meters. Now you might be saying, wait, that's a joule. No, it's not. I know this is weird, because a Newton meter is a joule, but it's a joule when we're talking about energy. And we're not talking about energy here. Right? We're not talking about a force acting over a distance, like you apply a force and you lift a box over up in the air. Right? We're talking about a force acting a distance away from the axis of rotation, which causes something to rotate. So yes, it's the same units as a joule, but no, it's not a joule. It's not energy units. It's just Newton meters. For those of you that have done enough work on cars, the English units for this may be familiar to you. It's called the foot-pound. Right? So it's pounds of force, how many feet away. Right? So a foot-pound. This is just a Newton meter. It could be a meter Newton too, I guess. It doesn't really matter, right? Either way. But a Newton meter are the units, and that's where we tend to leave them. Now remember, a Newton is technically a kilogram meter per second squared. The force required to make a 1 kilogram object accelerate at 1 meter per second squared. So the units of torque are actually kilogram meter squareds per second squareds, if you want it in base units. There is no fancy name for a Newton meter. In torque, they just leave it as a Newton meter or a foot-pound. Torque is a vector. As we saw, there is a direction to it, right? And we're going to define this the same way we defined angular velocity. and angular displacement, which is that counterclockwise rotation is positive and clockwise rotation is negative. And again, you can use a right hand rule. You can curl the fingers of your right hand in the direction of rotation, stick your thumb out. The vector actually acts in the direction of your outstretched thumb. So notice if you do counterclockwise and rotate your fingers in the counterclockwise direction, make sure it's your right hand, not your left hand, otherwise everything's backwards, and your thumb points up. Up is positive. Rotate your fingers counterclockwise and your thumb points down, right? And that's, rotate your fingers clockwise, right? And your thumb points down, and that's negative. So the right hand rule is just a way to help you remember, right? It'll come into some of the vector algebra we're going to do in a few days as well. So again, like angular velocity and angular displacement, we rotate around the vector. Right? We can't really point it in a particular direction because of the way that it's rotating. Right? So instead, we rotate around rotational vectors. So all the problems that we've done thus far, what we've looked at and what we did in the lab, right, and actually what we're going to do for another day or two here, the force is always perpendicular to the lever arm. Right? There's a nice right angle there. Well, there's no reason that that has to be true. Right? There's no reason the force has to act perpendicular. Right? Let's say we pulled at an angle instead of hanging masses from that equal arm balance. It could still make it rotate. It could still provide a torque. But then the question is how much torque if it's at an angle to the lever arm instead of perpendicular? Well, that's something that we'll get to in a day or two. Okay? Right now, we're going to focus when those are perpendicular to one another.